Alright, in this tutorial I'm going to show you how to use this formula to find the voltage difference between 2 points B and A in space. It is equal to the negative the integral from A to B, the field dot dr. This is the definition, theoretical definition of the difference of potential between 2 points. We are going to use this equation to evaluate what is the potential inside this solid sphere completely charged. It is an insulator, so we expect the charge to be inside. So what's the potential inside and outside? So since this is an insulator, the field outside is given by this equation, so we know the field. The field is the charge Q times the constant over R squared. We did this using Gauss. So in this exercise, if you know E, can you find the voltage? This is what we are going to do. Inside the field E, we have determined this also using Gauss law to be K, the charge Q, over R cubed and R. So it's linear inside. So two different expressions of the field inside and outside. And so let's start with outside. That means here, we are here, outside the sphere, the little r, the variable, is larger than the radius of the sphere under consideration. So we are going to apply or say what is the difference of potential between a point that is further away, infinity, and position r somewhere here. What is it? Well, that is VR, that's final position, minus initial infinity, you have to start way back, infinity, equals minus from infinity to R position, EDR. So now, we can switch this negative sign and the answer of the integral. The infinity becomes here, and this is R. And this is the expression of the field outside, which is this one. Now all done, the integral is minus 1 over R, and so this is 0, and this is the expression of the potential outside the sphere. Clearly it is hyperbola 1 over R. So that is the field outside. Now what is the field at the surface? Well, at the surface R becomes just large, big R. So this is the field at the surface. Now let's investigate the field inside. The potential inside. Potential inside the non-conducting material. So I'm going to start from the surface and travel to position R and see what is the voltage difference. So the starting point is, or let's go from this point to the surface, probably this way. The starting point is R, the end point, the surface. How does the voltage change when you go from R to R? So that means V, the surface, minus V position R was starting point, so we're moving outward, equals minus the integral from, so R to R, the surface is R, and then this is EDR, and E, we said this is the equation of E, this one here, so that is K, let's remove this one, obviously. So this is K and the Q over R cubed, and then R the R. Now before we do that, so I can multiply by negative both sides and switch this, so this become positive and this one minus, so I have VR. You are going to see why. Minus Vs I just brought this sign here. It's same thing. Now because I need VS to add the other side, VS is here, this one. So now the integral here is just K, the Q over R cubed. That's the constant I put outside, and the integral of R dr is just R squared over 2. I'm going to put 2 outside, and this is between, this is square. So this is between R and little r. Now what is this? It is K Q over R cubed, 2 of course. So this is R squared, that is R squared, minus little r squared. That's 6. This is not cubed, this is squared. All right. See if I can. All right, close. Now this VS, now I can probably do some change. So the VR, I'm going to bring the VS, this one here, the other side, and factor out everything. So that will be K Q over 2 R cubed, and then times R squared. Okay, times R squared, plus the VS, this one, which is KQ over R, KQ over R, then minus this quantity, which is KQ over 2R cubed, and then 2K, then R squared. This is 2 again. Somehow I'm having trouble writing 2. There you go. So you see here I can write something like this. This is here 2. This is 2, and this is 2. So same denominator. Here R square R cube, I lose this one. I'm left just with R. So KQ to R, 2KQ to R. Same denominator, that is 3K Q to R. The combination. And this is minus, I have K Q to R is say, which is the same to, and then I have R squared over R squared. You see R squared, R cubed. That is the VR. Now let's make small arrangement. That's small arrangement. And so we factor out KQ to R, so that is K. Alright, I'm going to write, I'm running out of time, so let's read the red and give you the answer right away. So I put this quantity here and this quantity outside. So the VR is equal to K Q to R, and then I have 3 minus R. Let's fix it. So 3 minus R squared over large R squared. So that's the potential inside the non-conducting sphere. Notice something interesting. When R equals 0, that means here, what do we have? This is 0. So I'm going to write here somewhere V0. What is it? It's not 0. It is K, a Q. I left with 3 and 2R. Unlike the field here, it is 0. So the field at the center is 0 because R equals 0, but the potential is not. And we are familiar with this situation. Now, in terms of a representation, I can do this. So at R, so here I have a constant, so surface, and then at the center, somewhere here, let's use the red, it's a parabola, open up parabola, like this, and then 1 over R. This is 1 over R, and this is minus x squared or minus R squared. So a little bit complicated potential, but this is how it works. So this is minus R squared. So this is a branch of parabola from the center. This is center. So the surface is constant, then it will vanish 1 over R. So this is how we use this formula. The definition of the voltage difference between 2 points is the negative of the integral the field along the path, and we're able to find the voltage.